Yes, sir.
So-
Alhamdulillah.
Sorry, we were disconnected multiple times because of electricity failure, and the computer was taking a bit longer to sign in. So now let's resume the class. Previously, we were talking about uh, electric field intensities, right? Today we want to expand the results little more, and I want to give you the concept of flux, right? As you said previously, when you separate charges, there exists a force between the two charges, right? That force is defined by Coulomb, right? Called as Coulombic force. But but because of one charge, if you are interested to measure the intensity on the another charge, you can also do that, right? So there exists a force, there exists electric field intensity. Now, how this electric field intensity moves around, how it creates the field, right, where its effect is there, right? For that purpose, we want to study the concept of flux and the flux density. Flux, more simply, by flux we mean flow, right? So if we say electric flux, so we will say electric energy flow, electric field intensity flow, or somehow we try to build the concept of showing how the electric field energy exists around a charge, or how the electric field intensity will, or how the electric field will move around, how it will exist in different directions. For that purpose, we are introducing the concept of flux. Okay, so and then for example, if I have this positive charge and the electric field is moving around from it in all possible directions, but if I take a certain unit area, for example this one, say this is some unit area, so how much intensity is going out of this area, how much intensity is leaving out of this area, that intensity, that flux, how much flux per unit area is called as flux density. Okay, that in flux which is flowing through an area, right? Area in space, for example, or area of any object, right? So electric flux flowing through certain area is called as flux density, right? Uh, do you get my voice clearly, by the way?
Yes, sir.
So electric flux moving or flowing out of or flowing into a certain surface area. So it's called as flux density. So flux density is flux through unit area of surface. Okay, unit area of surface of object. Okay, or flux through. By through we means moving out or moving in, right? We mean both. Okay, so flux is the flow. Now imagine if imagine uh, that we have a fluid flowing through a rectangular pipe. Say some fluid is flowing through a rectangular pipe, right? a fluid is flowing through a rectangular pipe. So how much fluid pass through this area, how much fluid pass through this area is called as flux density. Okay, if you change the direction of flow, if you change the direction of flow, uh, if you change the direction of flow, this is the direction of flow, and remember, area is a scalar quantity, right? Area is a scalar quantity. Area area is a scalar quantity, right? But but in this course, we assume its direction also. Okay, and the direction is perpendicular to surface. Okay, direction of the area is perpendicular to the surface. So if say this is the surface, right? So its direction will be perpendicular to it. Okay, will be perpendicular to it, normal. So the direction of the area is normal vector to that plane containing the area. Okay, so if the flux flow and the direction of this surface or sheet, if they are in both direction, you will get the maximum flux density. But if flow is in this direction and you slightly tilt the surface through which water is flowing, this is the normal direction. So then, depending on this angle, the flux density will be reduced accordingly. Okay, so that was a little definition of flux and the flux density, right? Uh, so we need to associate direction with the surface area element when we find flux due to a vector quantity E. All right. So primarily area, as I said, is a scalar quantity, but in this course we will associate direction with the surface area when we find the flux due to a vector quantity E. The direction is outward, normal to the surface. Okay, direction is outward, normal. For example, this is the surface, this will be its normal direction. Okay, this is area, surface area, right? Okay, now assume we have some positive charge uh, right here, right at the center of a certain sphere. You can see this blue sphere, you can see that, right? It's a sphere just like a football, right? So we assume there's a charge at the center of this sphere. Okay, so how much electric field will move through the surface of the sphere? For that purpose, we need the definition of the flux density. Okay, now suppose this is our point of interest, right? This one, this is a point of interest. Okay, this is the point of interest, right? uh, Here we want to find the intensity because of this positive charge. So intensity will be in this direction. Okay, and how much intensity will be here? E will be equals to, suppose this is charge Q, this one, so it will be Q divided by that constant 4 pi epsilon naught, and this r r square, r square, yeah, r square. So this is the intensity right here at this point, and this is the direction r cap, in the direction r cap. Okay, unit vector r, we denote this by r cap. Okay, okay. Now this line is going to make an angle theta. This line is going to make an angle theta. And you know, if I try to find a little differential area here, okay, uh, if I try to find a little different, so say the point comes here slightly. So what is this line? What is this angle? It's d theta. Okay, it is d theta. Okay, this one will be d theta. Okay, similarly, uh, if uh, if this is projected downward, here is rho, and it's making an angle phi. Okay, it's making an angle phi. Okay, okay, so if it's making an angle phi, then there's another angle, right? So this new position, this one is somewhere here, so this rho will come here, and what is this angle? It's d phi. So you have this arc, you have a secondary arc here, here. Okay, so this was the arc made by d theta, this is the arc made by the d phi, and this will give you the differential surface area. So how much flux is going out through this differential area? How much flux is going out of this differential area, right? That we need to calculate. Okay, so so I'll shortly show you little visuals of this phenomena. So how much intensity? This intensity at this particular point is E equals to Q divided by 4 pi epsilon naught. So how much flux is there? Flux equals to uh, the electric field intensity dot ds. ds is this differential area on the surface. This is ds. Okay, this is ds. Shortly I'll show you how this is going to work. Okay, so look, a little differential change in theta, this arc, this little differential change in theta. Okay, uh, this is this arc is how much? This arc is made by, this yellow arc is made by d theta. This yellow arc is made by d theta. Okay, we can also have this green arc. Once you move from here to here, the green arc is made by this point and this point, right? So we have the green arc, we have the yellow arc, right? We have the green arc, we have the yellow arc. Okay, yellow arc is made by yellow arc is made by d phi. The green arc is made by d phi, this one. Okay, so we have this yellow arc and then we have this green arc. So now how much is the total area made by the yellow arc and the green arc? This area, this is how much? This area is ds. Okay, this ds. And if you remember from our week number 1, if you remember this ds, or from this diagram, the ds is how much? As I said, we are going to take this area as a vector quantity. So ds is how much? It's the yellow arc. Yellow arc is how much? Yellow arc is r d theta dot the green arc. The green arc is how much? Green arc is r sine theta. right? R sine theta, how much? D phi. Okay, so this is already known to us. So ds is r square sine theta d theta d phi, and you can see that this ds in this little animation is shown here. Let me remove my writing from here, and so see you can see the actual phenomena in the diagram, right? So we have r square sine theta d phi. This is our ds. So flux is the surface integral E dot ds. Okay, flux is the surface integral E dot ds, which is the surface integral E is q divided by 4 pi epsilon naught r square dot ds. And ds is how much? R square sine theta d phi. Okay, so r square goes away with r square, right? Uh, R square goes away with R square. So let me remove my writing so you can see the equations more clearly. So R square is Q over 4 pi R square. This R and this R, they go away with R square. Charge is constant, 4 pi epsilon naught is constant. So you knock out some of the constant out of the equation. So Q over 4 pi epsilon naught R, they are constants. D phi, d theta and d phi, they are the variables. So you have this d phi going from 0 to 2 pi, this is 2 pi, sine theta 0 to pi, this is 2, and this goes away with this one, and uh, integral d phi from 0 to 2 pi is of course 2 pi, and integral sine theta from 0 to pi is 2. Of course it is 2. It is sine of pi minus sine of 0. Okay, so which will make it equal to 2. Okay, so this is going to be this entire thing is 4 pi. This entire thing is 4 pi, and this 4 pi will go away with this 4 pi. Okay, so uh, what you left is q over epsilon naught, so our flux is E dot ds equals to q by epsilon naught. If I still try to bring this epsilon naught here, so now uh, our flux will be equal to uh, integral surface integral epsilon naught into E is d dot ds, which equals to charge enclosed. Okay, so here what we said, epsilon naught into electric field intensity is equal to d. Epsilon, this is electric field intensity, and this one is electric flux density. Okay, so one is electric field intensity, the other one is electric flux, density. Okay, one is electric field intensity, the other one is electric flux density. Okay, uh, uh, d is what? D is electric flux density. Just focus on these definitions. Okay, it's a vector quantity, it's a flux density, it is electric flux passing through certain area, unit area. So D is the electric flux passing through certain area. Okay, so it's psi. I will call this kind of flux as psi. Okay, psi electric flux. Phi, the flux is charge divided by epsilon naught. Okay, phi. This is a little difference. Phi is charge divided by epsilon naught. Psi is simply the charge. Okay, so if I try to bring it here, okay, okay. Uh, so a little definition here. Okay, you need to focus on this definition. Acha, look here again. We call psi equals to charge enclosed. This is called as the Gauss law. This is called as Gauss law. So what it means? It means the charge enclosed is this one. The charge enclosed is this one. Inside that surface, inside that football, or inside that spherical object, that is the charge enclosed. And how much flux is moving out of that surface is the psi. A very interesting equation. Why it is so interesting? Because uh, this quantity is non-physical. It doesn't have mass, but this one is physical because it has mass. So charge has a mass. Mass of mass of charge is how much? 9.11 into 10 to the power minus 31. If it is electron, remember, kg. It has a mass of electron. Charge can be positive charge, charge can be negative charge. Okay, and mass of proton is nearly 1,000 times mass of electron. So 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 charge is a physical quantity. It has a mass, but electric flux doesn't have a mass. So it's a little interesting equation, especially at that time when like in the 16th century, when the era of the Gauss and the Faraday and the Maxwell, where they don't have uh, such huge instruments to measure masses and to measure the flow of electric field intensity. That was such an amazing equation at that time. The equation, the relationship still is valid here this day. The theory presented in this equation is still valid, and it verifies many physical phenomena. So this was the Gauss law. Okay, this was the Gauss's law. So what is the Gauss's law? The Gauss's law says if you take this um, flux phi, it's the surface integral E dot ds, which equals to charge enclosed divided by epsilon naught. That's the Gauss's law. Okay, and this one is also the Gauss's law, right? This one is also the Gauss's law. So if you bring this epsilon naught here, you bring this epsilon naught here, it's just become the same, the second equation, this one. Okay, any question here? Anyone? Any question? Any question? Hasib, any question here? No question.
No,
No,
sir.
sir.
Uh, okay. Do you understand this phenomena of the electric flux?
Yes, sir.
Yeah. Uh, we said we said we have charges. You remember? We said we have charges, right? You say we said we have charges. You remember? When you separate the charges, we end up on the Coulomb's force, and we end up on electric field intensity. But now we want to see more detail about the electric field intensity. So what we did, we introduced a new term called as flux to show the flow of this electric field intensity. And then we took the definition of flux density. Okay, and then we went through this little derivation, and in the process we 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 found a new law called as Gauss's law. What the Gauss's law tells us, it's such an interesting law. uh, it the Gauss's law and the Faraday's law of static charges, very similar, they are almost discussing the same concept. What the Gauss's law says, it says if in a certain object there is a charge, then that charge is equal to the total flux leaving that object. Simple as that. So, my question is, uh, there is a little question. What is unit of electric flux? What is the unit of electric flux? Anyone?
Weber, sir.
Weber?
Weber.
Okay, no, wrong. Yes, Rafi. What's the unit of electric flux? Rafi, you want to ask something? Rafi Latif, you want to ask something?
No, sir.
Okay. What's the unit of electric flux?
Newton meter square per coulomb.
And what is that? Newton meter square per coulomb. What is that?
Volt per meter.
Volt per meter? No.
Volt meter.
Volts per meter?
Voltmeter.
Sir,
No.
voltmeter, sir.
No. Why should be volt per meter? Why? Why should
No,
be
sir, voltmeter.
volt into meter?
Yes, sir, voltmeter.
Yes, sir. Volt multiplied by meter.
Volt multiplied by meter. So volt multiplied by meter is the unit of what?
Sir.
Electric flux.
वो इलेक्ट्रिक फ्लक्स का यूनिट है या इलेक्ट्रिक फील्ड इंटेंसिटी का यूनिट है?
Electric flux.
इलेक्ट्रिक फ्लक्स का यूनिट है,
Flux का सर voltmeter.
वोल्ट मीटर इलेक्ट्रिक फ्लक्स का यूनिट है।
Yes sir.
Yes, sir.
दोबारा थोड़ा सा गौर करें।
सर ये आपकी स्क्रीन गायब हो गई है सर।
स्क्रीन गायब हो गई है। लेट मी चेक
Yes,
दैट।
sir.
कहाँ से गायब हुई है? लेट मी चेक। ओके
Okay, sir.
अभी आ रही है नजर?
Yes, sir.
Yes,
आ रही है
sir.
सर।
आ गया।
लेकिन मेरी राइटिंग का अच्छा है, आई गॉट देम बैक। ओके
है इधर ही है सर।
Sir, Tesla.
नो
सर वेबर ही होता है सर।
टेस्ला तो डेंसिटी का
न्यूटन पर कूलम सर। न्यूटन पर कूलम।
नो
सर न्यूटन
सर वोल्ट पर सेकंड।
नो।
कैंडेला।
Look here. What is psi? Psi is what?
ऐसी पे
What is psi? Psi is the electric flux. What is Q? Q is the charge. So, what's the unit of charge?
Coulomb.
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 Unit is coulomb, right? Unit is
Coulomb.
coulomb. Yeah, of course, they are equal. They are considered as equivalent quantities. Though charge is physical, it has a mass, but electric flux doesn't have a mass. It simply is the flow. Somehow it will tell you the flow of energy. Somehow. Indirectly it's going to tell you the flow of energy. That's so interesting. they relate two things. Uh, they related two things. One which is physical, the other one which is not physical. Then upon such a amazing relationship here. Okay, so Faraday, Faraday, Faraday worked a lot. Faraday worked a lot on Faraday's experiment, right? Based on the relationship shown by the Gauss, Faraday worked a lot, and he did many experiments on this law of the Gauss, right? So this is the Faraday's experiment. This is the Faraday's experiment. What he did, he took a sphere, okay? Faraday took a sphere. This is a sphere, okay? And he charged. Faraday charged this sphere, okay, with positive charge, okay? So Faraday charged this sphere. And what he did, he brought another sphere. This was the first sphere. This is the second sphere. He placed a second sphere around the first sphere. And he observed again, Faraday observed charge on second sphere. He observed charge here. He observed charge here. This was so interesting, right? So initially Faraday thought that the charge from the inner sphere has moved to the outer sphere. That was the initial perception of the Faraday. Okay, but then he did what? Then initially, this was initially, okay, initially. Then Faraday put dielectric between two spheres, and he repeat the experiment again. He put this dielectric, he put this dielectric, right, plastic sort of material. He put it over there, and then again he observed charge on the outer sphere. Now since he arranged a dielectric between the two spheres, he thought, he believed that this charge from the inner sphere did not jump to the outer sphere because of the dielectric. Charge cannot move through a dielectric. So why Faraday put a dielectric? Because he was confirming whether this charge from the inner sphere has moved to the outer sphere or it is something else. So for that purpose, he put a dielectric between the two spheres. And he concluded that the charge from the inner sphere is not going to move to the outer sphere. But he said something has moved from the inner sphere to the outer sphere. So at that time when there was no big laboratory instruments, no accurate laboratory instruments, he called this phenomena as the displacement. He said something has displaced from the inner sphere to the outer sphere. So he called this phenomena as the displacement. Then later on he called it as the displacement density. Okay. Now actually what happened, if we consider this tiny little region, okay, this is, if I try to zoom this, if I try to make it bigger, okay, if I try to zoom this, if I try to zoom this little region, okay, you know that this positive charge, this negative charge here. Now when this positive charge comes, when this red positive charge sends electric field towards the outer sphere, what happens? The negative electron comes to the inner surface, leaving the outer surface positive, right? So this goes away, this thing goes away. So the inner layer becomes negative, the outer layer becomes positive. So if I try to zoom this, okay, what happens? The inner layer becomes negative and the outer layer becomes positive. This is what happens in reality. But Faraday at that time couldn't recognize this is happening. So that's why he gave this a very rough name called as displacement. Now we know that this is because this entire thing occurs because of this electric flux. This is electric flux. Okay, so it happens because of the electric flux. Okay, any question here? So that was the Faraday's experiment. Go through this Faraday's experiment. And read it out from the book. The inner sphere has a radius of A. So what is the area of the inner sphere? Inner sphere area is how much? Inner sphere area is how much? Anyone? कौन बताएगा? इनर स्फीयर का एरिया कौन बताएगा? 4 पाई a स्क्वायर. आउटर स्फीयर का एरिया कितना है? आउटर स्फीयर का एरिया कितना है? 4 पाई.
Sir, 4 by B square.
B square.
By B square.
Okay. Now look here. Electric. What is this D? It is the electric flux density. Electric flux density of the inner sphere is how much? Electric flux density of the inner sphere is how much? Inner sphere has a charge Q. It's Q divided by 4 pi. बताएं? 4 pi
A square, sir.
A square. And what is D of the outer sphere? Q divided by 4 pi
B square.
B square. Q inner is greater than D inner is greater than D outer. Yeah? ऐसा ही है ना?
Yes, sir.
Okay. And D equals to epsilon naught E. So E inner is greater than E outer. चार्ज एक जितना है, बट इलेक्ट्रिक फील्ड इंटेंसिटी इनर स्फीयर की ज्यादा है आउटर स्फीयर से. ऐसा ही है ना?